For more complex linear systems, it is convenient to represent them as state space models. In the state space form, the variables are written as vectors, and their coefficients are written as matrices. Here, x is what we call the state vector. X dot is its time derivative. The state vector is the vector of state variables. The vector u contains the input manipulated variables, and the vector d contains the input disturbance variables. The vector y is the output vector of measured variables, which can be computed from the vector of state variables. The matrices A, B, E, and C are coefficient matrices. Then the Laplace transform of a state space model written like this is an algebraic expression, and the output y is related to the inputs u, the manipulated variables, and d, the disturbance variables, with two transfer function matrices, g sub p for the manipulated variables and g sub d for the disturbance variables. The transfer functions contained in the matrix g sub p and g sub d can be derived from the coefficient matrices using a little bit of linear algebra. Here, the capital I is the identity matrix. Let's consider an example that we can write in the state space form. Here we have a mixing tank with two inlet streams. There's a hot stream with flow rate WH and temperature TH, and a cold stream with flow rate WC and temperature TC. We'll assume that the tank operates at constant density and heat capacity. And then we'll ask, how do the temperature T and height h change with time? So T and h will be the output variables from our model. The level in the tank can be determined from a mass balance, and the temperature of the fluid in the tank can be determined from an enthalpy balance. Performing the degree of freedom analysis, we find that there are three constant parameters that appear in this model: the density, the heat capacity, and the cross-sectional area of the tank. That leaves 7 additional variables: the tank level h, the mass flow rates of all three streams, WH, WC, and W, the temperatures of all three streams, T, TH, and TC. Of course, we have two equations, the material balance and the energy balance, so our number of degrees of freedom is 5. Since there are two equations, we can have two output variables. We'll choose h and t, and for now we'll label the remaining 5 variables as disturbance variables. We'll assume that none of these are manipulated variables. To take the Laplace transform of the material balance, we'll first define the perturbation variables, subtract the steady state form of the material balance from the dynamic form, and then substitute the perturbation variables into the dynamic equation. Remember that writing this in terms of the perturbation variables simplifies taking the time derivative, so that we don't have the initial condition appearing on the left-hand side. The transfer functions relating the inlet flow rates and the outlet flow rate to the level in the tank, not surprisingly, are integrators. For the enthalpy balance, we cannot take the Laplace transform because this is a nonlinear equation. This ODE contains nonlinear combinations of our disturbance variables, like WH times TH and WC times TC. First, let's simplify the energy balance by substituting in the material balance. This eliminates Tref from the right-hand and left-hand sides of the energy balance equation. It also eliminates W. Next, we'll use the Taylor series expansion to linearize this nonlinear equation and substitute in the perturbation variables. The right-hand side contains partial derivatives evaluated at the steady state multiplied by the perturbations in TH, TC, T, which is combined in these two terms, WH, WC, and H. Now, because each of those partial derivatives is evaluated at the steady state, represented by the variables with the bars, they become constant coefficients. We can take this into the Laplace domain and move all of the t prime variables over to the right-hand side of the equal sign. The term highlighted in green here is the steady state form of the energy balance, and since there can be no accumulation of thermal energy at the steady state, then this term is equal to 0. After moving all of the terms that contain t prime to the left-hand side of the equal sign, we can solve for perturbations in t as a function of perturbations in each of the other remaining 4 perturbation variables. That takes a little bit of algebra in the Laplace domain, but we can see that each of these is a first-order transfer function, and they all have the same time constant tau, which is the residence time for the tank. Now, we could do the same thing going back to the time domain and writing the model equations in the state space form. The state variables are the height perturbation and the temperature perturbation, since those are the things that we have time derivatives for. In this case, these are also our output variables. So y and x are the same thing, and y is related to x by a matrix C that should just be the identity matrix. Since we don't have a control system here, we don't have any manipulated variables u. All of the input variables are disturbance variables. So that means we can ignore the matrix B because u is the empty vector. Next, we write the time derivatives of the perturbation variables as a sum of the effects of the state variables and the effects of the disturbance variables. The equation for h doesn't contain either h or t, so the coefficients in the first row of A are 0. Furthermore, h doesn't appear in the simplified equation for dt prime dt, so that coefficient is also 0. But t prime does appear in that equation with the coefficient minus w bar over rho ah, or minus 1 over tau. The matrix E determines how each of the disturbance variables, wh prime, wc prime, w prime, th prime, and tc prime, affect each of the state variable derivatives, dh prime dt and dt prime dt. The temperatures do not appear in the material balance, and only the two incoming stream flow rates and temperatures appear in the energy balance. The effluent stream was eliminated. Now we can take the Laplace transform of our linearized state space model. The state space, or the matrix and vector notation, is obviously much more compact for representing this type of multiple input, multiple output model. Furthermore, when we write the state space form in the Laplace domain, we can use these matrices to derive the transfer functions. For example, the transfer function matrix GD can be found using this equation, and the result is consistent with what we found before. The matrix of transfer functions relating the manipulated variables to the output variables y can also be found using a similar equation, replacing the matrix E here with the matrix B. Our model had no manipulated variables, so we don't need to find those transfer functions. In Chapter 6, we talked about the dynamics of processes that include numerator dynamics. The term numerator dynamics is used to describe in the Laplace domain functions of s in the numerator of a transfer function. We looked at two examples, time delays and zeros of the transfer function. We also showed how time delays can be used to model higher order dynamics. Here we saw that complicated transfer functions containing higher order numerator and denominator polynomials can be approximated using FOPTD and SOPTD models. We'll use this strategy throughout the rest of the semester to simplify more complex transfer functions. Transfer functions can also be used to model processes that have multiple inputs and outputs, just as they can for models that have only a single input and output. Writing models in the state space form provides a convenient representation of MIMO, or multiple input, multiple output ODE systems. And furthermore, once we have the matrices of coefficients in the state space form, we can use simple formulas to derive the transfer functions.